Hello folks, today in this video we're going to be talking about optics. Specifically, we're going to be talking about the ray model of light and how we can use optical devices to change the direction and the properties of light. Let's go ahead and get started. So optics is the study of light rays as they interact with matter. Now we've already seen different ways that light can react. Remember, with matter, you might remember us discussing light rays that are incident on a boundary. When a light ray is incident on a boundary, it can either reflect off of that boundary, and we know it comes back at the same angle it came in at. It also can refract, which means the light can bend as it passes into that new medium, or it could, of course, be absorbed by that boundary there. So boundaries, definition, is any intersection between media. Well, we actually have a lot of different boundaries when we are thinking about optical devices in our world. For example, if you have a pair of glasses, which I don't have mine with me right now, there's a boundary between the air and the glass as the light comes into the lens, and then another boundary as it leaves the glass and goes out. And so we have to consider what happens to light at those boundaries when we're designing a device like a piece of glass. In general, we're going to take the ray approximation of light, which is that light travels in a straight path in a medium until it encounters a boundary, and only then are we going to consider the light changing from there. And so we call that the ray approximation, which is used to represent a beam of light. Now remember, light is complex. It can be like a particle and a wave. There's lots of things going on with it, but we're going to use this ray approximation for optics here. And all a light ray is an imaginary line drawn along the direction of travel of a light beam. Now, we've already heard about reflection. The law of reflection states that when light reflects off a boundary, the incoming angle, the angle of incidence, is always equal to the angle that it comes out at. So if you have a nice flat mirror here, you can imagine different rays of light coming down and striking that mirror, and then it would reflect off at that same angle, and then it might go ahead and reach some observer up there. That's supposed to be a eye to represent that there. Now, because an object doesn't just emit one ray of light, what happens is that you will see the reflected light and it will appear as if that light is coming from a single point. That is what we call an image. An image is formed by the real or apparent intersection of light rays. In general, to find an image, we need to imagine at least two light rays that are coming from an object, striking some boundary like a mirror or a lens or something, and then going to some observer who is going to be seeing that there. So that's what an image actually is, and it's all based on reflection. Now, I want to talk about real versus virtual images. What does that mean? A real image is produced by the actual intersection of light rays. So this is a curved mirror here, and you can see that if I imagine two light rays coming off of this mirror, they appear and actually do intersect at that point. This light would focus right at that point there. That is what we would call a real image because it's formed by the actual intersection of light rays at that point. A virtual image is produced by the apparent intersection of light rays. What do I mean by that? Well, this picture is actually a great picture for a virtual image. The reason why we say that's an apparent intersection is these light rays coming from this point here, they're not actually intersecting at like one single place. In fact, they're spreading away from each other. But what happens is they appear to be spreading away from a point behind this mirror. So if you've ever looked at yourself, for example, in a flat mirror, you see an image of yourself in that mirror. Does that mean the light is actually coming from behind the mirror or intersecting behind the mirror? No, not at all. That's a virtual image that appears in that space there. This actually becomes important if you were to use optics to project something. For example, to use a projector. A projector uses real images because you can project an image onto a screen. Why? Because it's real. There's actually an intersection from that there, but you cannot use a virtual image to do that. So a flat mirror would never project an image onto another thing, but a curved mirror like this one here actually could, which is pretty cool. So let's talk about those flat mirrors that everybody knows. Everybody's seen a plane mirror. You see them in every restroom in the US. You probably have some at home. It's the simplest type of mirror. So we either call it a plane mirror or a flat mirror. For plane mirrors, they have a unique and nice property, which is that the distance is always equal the image distance is always equal to the object distance. What do I mean by that? If you are standing in front of your mirror at home and you're just trying to take a look at things, you can kind of test this, which is kind of cool. Look and see how far away you appear to be from that mirror. Let's say you're 1 foot away from that mirror there. Your image will appear to be exactly as far back in the mirror as you are in front of it. And so that'll be about 1 feet as well, which is pretty cool. So image distance is always equal to the object distance. The image then that you see is always upright, which means it's like right side up as opposed to being upside down and flipped. It's always virtual. Virtual means that it is formed by the apparent intersection of light rays, not the actual, and the same size. In general, flat mirrors do not change the apparent size of the object, but they do mirror things, as is left and right is shifted. So I'm holding up my right hand here, but it looks like it's on my left side. I'm holding up my left side here and my left hand, and it looks like I'm on my right side. So image is flipped there. That is contrasted with curved or spherical mirrors, which you might have seen before, either at like a, playground funhouse or on your car, or maybe you've seen some of these in stores or other different places there. A spherical mirror is simply just a mirror that has a shape that is like a cutout of a sphere. If you were to take a sphere and put a mirroring coating on it and then cut it apart, you would get curved mirrors that are called spherical mirrors. And there's two types. You got concave and convex. For a concave mirror, the reflective surface is on the inside of the mirror. The way I remember this is that you're looking at it and it looks like the mirror is caved in. So this is concave, caved in. A convex mirror, the reflective surface is on the outside of the curve. And so that's a convex one. So concave and convex. And they have slightly different properties in the way that they work. I wanted to find some important variables and important features of these mirrors. For a spherical mirror, you could talk about, first off, the radius of curvature. What do we mean by that? We mean if you were to take this sphere, r is the radius of that sphere. So they give you that distance, r. That would be the distance from there to there. So that's the radius of the sphere that makes that curvature mirror. And then c is a point. So this is an actual distance, and we're saying that this is a point. The center of curvature is the point that would be at the center of that sphere. Now, the radius of curvature isn't that important for mirrors. What's much more important are these two terms, the focal point and the focal length. This is also a point, the focal point, and that's the point where parallel light rays would be reflected into by a concave mirror or reflected away from by a convex mirror. So you can see here that there's these parallel light rays coming in and they are being focused right to that focal point. This is the classic, hey, I'm going to like go outside and try to light a piece of paper on fire using like a magnifying glass. That would be focusing that light onto a single point. That's what a focal point does. And then the focal length is simply the distance from the mirror, the very center of it, to that focal point there. So focal length and focal point are fairly similar, and you'll kind of hear people kind of use them interchangeably there. The principal axis is just an axis passing through the center of the mirror that goes through the center of curvature and the focal point. And lastly, there's a relationship between the radius and the focal point. That is that the focal length is half the radius of curvature of your mirror. Okay, so those are our kind of variables and definitions that we want to make sure that we get. Now, before we go any further, I want to mention two other terms. Those terms are converging and diverging. What makes these mirrors a little bit different is that one of them takes the light and puts it into a single point. The other one takes the light and makes it go and spread out away from each other. So this concave mirror is a converging mirror. You can see that the light tends to get closer together after reflecting off of that mirror. A convex mirror is what we call diverging. Not like that terrible knockoff Hunger Games movie, but like the light rays are actually diverging away from one of another. So diverging means that they go like that. This one then tends to form what kind of images do you imagine? Virtual, because virtual is when it's an apparent image where there's the apparent intersection of light rays behind the mirror, whereas converging ones tend to make real images. There's a little bit of a sticky point there with the concave one because they can also make apparent or virtual images, but we'll get to that in a second here. Okay, so now lastly, let's talk about how do you find out where an image is. So to do that, we use a thing called geometrical optics. We're going to take a look at this two ways. The first one is going to be qualitatively using ray diagrams, and then the other one is going to be quantitatively using mathematics. So ray diagrams are a technique used to determine the location and magnification of an image reflected in a spherical mirror. This is a geometric argument. We are going to be drawing some lines and then using the shape of those lines to figure out where the image is. It's kind of a fun puzzle, I think. What you'll need, of course, is a pen or pencil, and you'll need some kind of straight edge that you can use to draw on. So here, our rules here are that you draw 3 rays from the same position on an object, and that the intersection of any 2 of those 3 rays locates your image. We use 3 rays because that way you can kind of confirm that you are correct with the first 2, because sometimes you can be a little off if you don't draw too well. Now, there's 3 rules here. I'm not going to read them out all together. Let's take them one by one and also do an example as we're doing that. So my example is going to be here. I've got a center of curvature, I've got a focal point, and I've got my mirror. I'm going to put a little object here. Doesn't matter what you want to do. Mine is going to be a person who's apparently very tall. There's my person, and they are going to be doing my rays here. I'm going to use some different colors, and hopefully that'll work out well. So ray number 1, it says, is drawn parallel to this principal axis and is reflected in line with the focal point F. So what that means is you'll take your straight edge here, and I'm going to start from the very top of my person, and you just want to line it up so that it's completely and perfectly parallel with that principal axis there. Once it reaches the mirror, mirrors reflect, and it's going to reflect downward through my focal point there. And you want to draw this line, give it plenty of space on the other side. Don't end it right away, because you never know how far out your image is going to be. So not perfectly straight, but good enough here for our work. Ray number 2, I think, is the hardest one to draw. It says, draw it to the point the principal axis meets the mirror and reflects by applying the law of reflection. So this one means you're going to draw it directly to the very center point of that mirror where it meets the principal axis. So that part's easy. Start at the top of your person, and then go ahead and go down. Sorry, guys. Down to the center of my mirror. So that's the beginning. To do the next part, though, it's a little tricky because I needed to reflect at the exact same angle out that it went in at. That's a little tricky, but what I found that helps me is I'll actually take, if I have a ruler, I'll measure how tall my guy is, and then I'll actually just draw like another copy of him down here at the same height. Because if you can think about it, it should go down and pass back to the exact same distance as it did coming in, because it's being reflected at the exact same angle. So I estimated as best I could there. And actually, I'll go ahead and draw this one with a little bit of a different color now. So sorry about that. And I want it to pass right to the top of that guy's head. And looks like it goes through there. So that's my second ray. And I'll actually just trace it here just so it's pretty clear that ray 2 is my one in blue. And where'd my second one go now? I'll redraw it, and that'll be fine. That way it looks a little bit better, actually. Okay, so ray 2 is now in blue. Now ray 3 then is drawn through the focal point and then reflected parallel to the principal axis. It's almost the exact opposite of ray 1 that we drew in. So we'll pick a different color. Let's do purple. And we'll come on down through the focal point and then hit the mirror. So right from the top of his head, through my focal point, and hit the mirror. And if I did this correctly, this being parallel should mean that this should all cross at the exact same point. Not bad. Could be worse. I think my line isn't even parallel, so it might have gotten a little closer if I had. But all this means is that the location of my image, my line went away there, but I'll go ahead and just freehand it in here a little bit. Oh, look, looks even better now. My image is at the intersection of those three lines. And if you wanted to actually calculate the distance, you could just take a ruler and measure it. That actually works with the mathematics. So this is how you find an image using a ray diagram. The other way you can find the location of an image is using two mathematical equations. The first one, called the thin lens equation, relates the focal length, f, with two different variables, dO and dI, where dO is the distance between the object and the mirror, and dI is the distance between the image and the mirror. You can also calculate this thing called the magnification of your image. Magnification means what you think. It means whether the image got bigger or smaller. And it's just a series of ratios. In general, if the height of the image, that's HI, is larger than HO, M will be larger than 1, and thus your image is magnified. It is bigger. If it is less than 1, then it is reduced. It gets smaller in size. And this is what we were talking about with a flat mirror. We had said flat mirrors don't make you look any bigger or smaller. It's the same size because your image distance is the same as your object distance for flat mirrors. But that's not true typically for concave and convex mirrors. An image is real then if it's on the same side of the mirror as the object. So we saw that back here. Image is over there. And it would be virtual if it was on the opposite side of your object. Lastly, we can talk about inverted if M is negative and upright if M is positive. What do I mean by that? This image, notice, I took the top of this guy's head and the image of it was formed down here. So my image would actually look like this. This would produce an inverted image. And in general, converging mirrors tend to produce real inverted images. This is kind of like how your retina uses an inverted image. So your lens produces a real image on the retina, which is a screen, and it's actually inverted. And your brain knows to flip that image to make it right side up so that you can see. So let's take a look at how this works mathematically. I've got a problem here. It says if an object is located 15 centimeters in front of a converging mirror whose focal length is 7.5 centimeters, where would the image be located? Well, we'll go ahead and use that first equation. 1 over f is 1 over dO plus 1 over di. So 1 over the focal length, 7.5, is 1 over 15 plus 1 over di. And solving for di here, it's not the easiest equation to use, so go ahead and give it a try yourself. But I actually get 15 centimeters. So funny enough, comes out to be the same thing. It's not always going to happen, but in this case, it did indeed. So this is a little faster than doing the ray diagrams, but is just a different way that you could do it. Next, if the object's height was 4 centimeters, how tall would the object be? We'll use our magnification equation, which is minus di over dO equals hi over ho. Plugging in, I get negative 15 over 15 equals hi over 4. So hi is negative 4 centimeters. So that means it would be the same size. The negative is just telling me that the image is inverted. That makes sense because I got a real image out of this one. I know that because this is positive. In general, if it's positive, it'll be real. And if it's negative, it will be virtual. Okay, folks, thank you so much for watching this first video on optics. Have a fantastic night and the rest